Let's talk about nitration of benzene. That's installing an NO2 group onto our molecule. We'll see the reaction conditions are nitric acid and sulfuric acid. We need both of these, and we'll see why in the mechanism. And in doing so, with these two reagents, we will end up nitrating our benzene. We'll put an NO2 on. And we're going to see we can do other things with that later. So first step, let's talk about the electrophile. In order for this to happen, we need NO2 plus as our electrophile. And we're going to see how we're generating that. So if we take a look at the nitro ion, or rather nitric acid, because this is acidic conditions, nitric acid is not as strong as sulfuric acid, so nitric acid is the weaker acid. So if we're going to see that what's going to happen with this is the sulfuric acid will actually go ahead and protonate your nitric acid, which is a little bit weird, I understand, because nitric acid is already a strong acid, but sulfuric acid is able to protonate it. In doing so, we're going to end up with now having our nitro group with a nice leaving group on it. And again, we have some weird stuff here happening. We have two positives in our molecule next to each other, and we have a negative elsewhere in the molecule. It's a giant mess. But all that needs to happen is we're going to close down our negatively charged oxygen and kick out the water. Water is a good leaving group, as we know, plus putting those positive charges next to each other destabilizes, so it's ready to leave. And in doing so now, we are left with nitrogen with two oxygens, double bonded to each one, with a positive charge on the nitrogen. And we will produce water as a byproduct. And of course, technically, we have our sulfuric acid anion, our bisulfate anion that's produced in the reaction. So, this is our electrophilic species here. So let's see, just like with any other electrophilic aromatic substitution, the reaction is going to follow the same set of steps. So we've now made our electrophile. So now it's going to get attacked by benzene, form a sigma complex, and then we're going to deprotonate. So as benzene finds this nitronium ion, here we go. Going to go ahead and attack. One of those two double bonds will pop open. Doesn't matter which one, because as we know, the nitro group has one double bond, one single bond, two oxygens. In doing so, we have now our cation. We have our nitro group, which we're going to just abbreviate NO2, but if we spread it out, we remember that we have a positive and a negative, positive nitrogen and negative oxygen in that group. I'm not going to draw the sigma complex because we can see that before it's just the resonance. Our dear friend water comes in. Water is a much stronger base than bisulfate is. And so our water comes in, grabs that proton, and we're going to close back down our benzene, restoring aromaticity. We're going to make hydronium, and we will have nitrated our benzene. Ta-da! And so we can install a nitro group as well. What's very useful about this, though, is that there's something we can do now that it's a nitro group. If we treat this with zinc and HCl, followed by sodium hydroxide, we can reduce this to an amine. In the first step, the zinc and the HCl donate the hydrogens and take away the oxygens. And in the second step, we're going to end up with a protonated amine because amines are bases. The sodium hydroxide is there just to get rid of the extra proton that'll be hanging around at the end of the reaction. And so we can reduce a nitro to an amine. This will be incredibly useful for us, synthetically speaking. Because having that amine there, we'll see, will allow us to do a lot more things than having a nitro group will. But that's something for discussion later. And so with this, we can see two kind of reactions here. In the first, we take our benzene, treat it with nitric acid and sulfuric acid, and we will end up nitrating it. However, if we take our benzene and react it first with the nitration reagents, and then do zinc and HCl followed by sodium hydroxide, we can put in an amine instead. So we have two more things to add to our toolkit here. So we can nitrate it, and then once it's nitrated, reduce it. The mechanism for the reduction is not important here. Really, since this chapter is on electrophilic aromatic substitution, this is the important mechanism. Forming your electrophile and then having that electrophile get attacked by benzene. That's the important part. And then, of course, having a base come and eliminate, forming our benzene again. And so, in this kind of video, these are the two reactions we want to focus on. So you can nitrate it. Once it's nitrated, you can reduce the nitro group to an amine. And that's going to broaden our synthetic toolkit quite a lot.